Our next speakers are Ian Butterworth and Ryan Benasutti, and they will talk about a cloud-native parallel data processing application in Julia. Please join me in welcoming the speakers.
Thanks, everyone. So for those who don't know me, I'm Ian Butterworth. You might know me for Julia stuff. I've done some things around kind of PKG and things like that I'll talk about a little bit. But I'm also CTO and co-founder of a medical device startup where we use Julia. And Ryan is our senior software engineer. So we're going to be talking about some uses that we have for Julia and some issues that we want to highlight. So the need that we're going after is in chemotherapy, there is a significant issue with the risk of the chemo itself causing hospitalizations. And the reason that that happens is that chemotherapy has a side effect of causing low white blood cell counts. And so the typical way that you have chemotherapy is in the hospital, you get your chemo dose, you get a blood draw to check that your white blood cells are high enough. Then you're sent home for 2 to 3 weeks. And in that time, you don't know what your white blood cell count is doing, but it will probably be dropping down to high-risk ranges and come back up. And then you go back to the hospital for your next dose and you get another blood draw. But the problem is, at home, you may have low white blood cell counts and develop an infection, which can trigger going to the hospital, can delay chemotherapy, or in itself be dangerous. So what can be done at the moment is really only extracting blood for analysis, and so typically that only happens at the hospital. But what we've been developing is a device for chemotherapy patients to take home called PointCheck, which is a non-invasive device. It can be used at home. It takes a few minutes to take a measurement, and it's cloud connected so that it notifies the care team if white blood cell counts are low, and enables earlier intervention if their risk is especially high. And the way that we do this is by looking through the skin in the region just above the nail, where is a relatively unique place in the body where capillaries flow parallel to the surface of the skin. So it gives us an opportunity to look at the capillaries from the side, and this is the type of video that we collect. So I'm hoping that you can see these on the screens. But what we're seeing here is the dark red blood cells and then the bright white blood cells going through those capillaries. So our device collects these measurements, and we've designed the device to work in the hands of untrained users. So it's a smart microscope, basically. And we've tested it with people that are completely untrained, and we've published some data on that, which you're welcome to look up if you're interested. But fundamentally, the way that the device is designed to work is collect measurements at home, upload those measurements to the cloud, analyze them, and send the screening information back to the clinical team, so that the clinical team can decide what to do if what's called neutropenia, so low neutrophil counts, has been sticking around for too long. The clinical team might want to administer prophylactic antibiotics or other things such as growth factors, which can stimulate the growth of white blood cells. So that's the data center at MIT where Julia was founded. And this is Building 36 at MIT, where Luca was founded, or where we started the project. So back in the day, we did a lot of our original code base. We were originally a small group of kind of machine vision type engineers and PhDs. And our original code base was MATLAB. And while we were at MIT, we were hearing of this cool thing that potentially could solve the two-language problem. And we were fortunate enough that when we actually spun out of MIT, Julia was good enough for us to start using it. So it became a really logical thing for us to start using. And we've been trying to help develop Julia to be even more helpful for us as well. So the two things that I'm talking about, or the two things in terms of Julia at scale that we have, are one being our kind of product infrastructure, which will exist when the product is out in the real world and analyzing real measurements, or we do analyze real measurements, but analyzing in a product sense. And that system will be continuously available, and it will be scalable and highly available. But what I'm talking about mainly today is our R&D setup. So we've done many studies, we've collected many measurements on people, and every time that we touch our Julia code base, we want to make sure that not just our unit tests and integration tests are passing, but that our diagnostic performance on our large data sets is adequate. So we've developed a system which can, so that a developer can open up a PR, make their changes, invoke a GitHub comment, go off, massively scale up the analysis of that, and post back a report giving us the diagnostic performance and a variety of rich kind of information. There's a lot of stats up here, but ultimately it scales up to having 600 EC2 instances at its maximum parallel at once, which, just to visualize, is probably this small slither of an AWS server farm. What we call Leucotester, which orchestrates this whole thing. So we have an S3 bucket. We spin up workers that grab from that S3 bucket, and those workers, as I said, could be 600 in number. And once they've analyzed those measurements, we'll send their kind of data-rich objects back to S3, and then from that S3 bucket, we have a single worker that then does kind of total analysis on those rich individual measurements, and then saves some information at the end. And the part that is really very slow, and we think has great room for improvement in the Julia side of things rather than our own code base, is the downloading and uploading of data from a single worker node. And that's what we're focusing on. So our objectives in this part of the presentation is to benchmark Julia's S3 data transfer performance, see what is actually the best option out there if you're doing this in a variety of different database dataset setups, and then figure out what's actually possible and what our bottlenecks are, and if there's something that we can help figure out and fix in Julia and the community.
Yeah. OK, so I'm going to talk briefly about our methods for this benchmarking, and then I'll get into the results that we have. So we have two data sets. The first one there is a copy of one of our actual data sets that Leucotester has processed, just so that we're getting results that are actually applicable to Leucotester. And so if you're seeing that weird number of 87 gigabytes, that's why. And it is split over quite a large number of objects. They're not all the same size. Most of them are less than 5 megabytes in size, which means that we'll get them in a single GET request. So that's not testing multi-part downloads, which is why we have our second data set, 10 objects, each one's 10 gigs each, so that we can test multi-part downloads. And then for software, of course, we're testing Julia with the familiar AWS.jl package and its two backends. We're also testing Cloud Store, which is packaged by Jacob Quinn that interfaces to lots of cloud data stores, including S3, with a brand new backend for that, http2.jl, which is a new exciting reimplementation of the HTTP package using the AWS CRT, which is a set of native libraries AWS publishes. And we'll see why that's important later. We're also testing against Go. As Ian said, we want to know not just what Julia can do, but what is a realistic goal for Julia to reach for. And Go, you'll see, will perform very well on all of these benchmarks. So that is a good point of comparison for us. And then there's a ton more variables that we are leaving out here. So if you want to see how this works, or if you even want to contribute your own benchmarks, because this is an extensible framework, you can do so at that repository. So I'm not going to spend too much time on these next few slides, but we just want to give you all an idea of the breadth of what we've collected. So each row here is a unique benchmark. We sample each benchmark 3 times on both data sets. And then for each benchmark, these are the types of metrics that we collect to make sure that the benchmark is doing what we expect, to make sure we're testing what we actually think we're testing. One thing to note here is on the top left, you see CPU usage. Go is around 8% CPU over the course of this benchmark. And in comparison, Julia is at like 50%, almost 60% sometimes. So that's hinting at some scheduler overhead we'll see later and room for improvement there. So here's a simplified view of our first data set. So this is 87 gigs over all of those objects on an instance which should be able to achieve 12.5 gig throughput to S3. We can see Go is doing very well near the theoretical limit for this instance. And in terms of Julia, our best option is Cloud Store with that new backend. And then the familiar AWS package with the HTTP backend is doing OK. It's maybe just over half of what we should be achieving on this instance. And then the downloads backend is not doing so well. Unfortunately, that's a theme throughout all of these benchmarks. Here's the other data set. So here we have 10 objects. Each one is 10 gig. And we have a similar distribution. And then one last slide to look at. Here we're running on that same data set, but we have a much larger instance. This instance should be capable of 100 gig throughput. Go gets close to that at around 85. And then Julia is about half that at 40 gig. Here, I actually have an open question to the audience. If anyone has observed a single EC2 instance achieving S3 throughput of 100 gigabytes per second, or gigabit, excuse me, then please let me know how you did that. AWS does document that this should be possible, but in all of my testing, I never achieved more than 85 gig. So if any of you know, please get in touch. So to summarize that, if you need lots of throughput in Julia, right now your best bet is going to be using Cloud Store with HTTP 2, though do note that is not quite production ready yet. So this is really like a call to the community to get involved and start trying out this package. It's in a pretty good state, and I know Jacob is using it internally, but now it's at a point where we need people in the community to start using it so we can get more miles on it and figure out any last issues there. If you do need something that's production ready, then just continue using the familiar AWS package with the HTTP backend. We also went in deeper on a couple of these benchmarks with some profiling to figure out where we're going wrong. With AWS and the HTTP backend, we're spending almost half of our time waiting on the libuv IO lock. If any of you aren't familiar, Julia's IO system is based on something called libuv, and it has a very large global IO lock in it. So when we're trying to do tons of concurrent I/O, we end up having a lot of contention on that lock. And that's the main reason that Cloud Store with the HTTP 2 backend can achieve much better performance, because it doesn't use libuv. It's using the AWS CRT, which has a totally separate I/O system. But even in that case, we're still spending a non-trivial amount of time in Julia's scheduler trying to figure out what tasks should be running instead of getting useful work done. So that's another point of future work. We need to keep profiling that, figure out what's going on in the scheduler. And then lastly, if any of you want to follow progress on HTTP 2 or on anything we're doing with a CRT, because it's not just limited to this, then you can check out the Julia Services organization where Jacob and I are collaborating on those packages.
Yeah, and so we also just wanted to talk about some of the tools that we're using along the way. So we'll talk about containerization, our source management, and profiling. And on the first point, something that's working really well for us as a company is to have an internal registry. So we use local registry to manage that, and we have actions set up so that we enforce that you can override it, but we promote people to do new releases for every PR merge, and we have that system fully automated to release those versions, and that's working pretty well for us.
Yeah, and I'm happy to get to finally announce that Trivi, if you're not familiar, it's a code and configuration scanner that can identify like vulnerabilities, secrets you may have committed, and it can generate reports like software bill of materials or SBOMs, which we do for like all the artifacts that we build in our CI pipelines. But finally, my PR adding Julia support to Trivi has been merged. So now if you get Trivy, the latest release, it will understand like what a project TOML file is and what a manifest.toml file is, and you'll see your Julia applications and all your dependencies in your SBOM. You will also see JLLs in there because they do have project files, but there's a little more to JLLs with the artifacts that they wrap, the sources those come from, and those licenses of those sources. And now these new JLL TOML files coming in Binary Builder 2. So there is some more work for me to do adding all that to Trivy, but it's at least in a usable state today. OK, so now we're going to move a bit to how we build the analyzer. So if you remember earlier where we had that diagram of we're taking data from S3, spinning up lots of servers, processing all that data, putting it back into S3. The code running on all those servers in parallel is what we call the analyzer. So we have this in a monorepo where we have the top level is the analyzer package, just a standard Julia package. And then in that we have another package which we just call service, which exists to take that analyzer package, which doesn't have any concept of like doing things over the network or processing requests, and we adapt that to work with a service-oriented architecture where it's like running continuously and receiving requests, and we bring all that into a Docker container. So the fact that we bring it all into a container gives us a good opportunity to optimize our startup time, which we could do with package compiler, but unfortunately, it takes like almost an hour to build that system image, and we would be doing that in CI, so that would extend our developers' iteration time, and it's not really worth the benefit because the amount of time that it takes us to analyze a measurement is much longer than the time we would spend in the JIT on the first invocation of this. So maybe that could change in the future with like Julia C stuff, but for now, not so much. And then two notes about anyone that is building Docker containers with Julia code in them. You should be sure that you're setting your Julia CPU target correctly, because it's probably the case that the server you build the container on has a different CPU architecture than what you're running it on. So like we build our container in GitHub Actions, and then we deploy it onto EC2. They're both running Intel processors, but for this number crunching heavy like numeric code, we really need to take advantage of all the local features available to our processor. So be sure to use multi-versioning with your Julia CPU target, set the appropriate ISA in there. And I hear it works with package images now. Sort of. Sorry, I put you on the spot, Gabriel. Yeah. And then the other thing is, when you install packages, you get the entire source tree of the package. You don't just get the project.toml file and the source directory. You also get things like the test directory, any build scripts they may have, other applications within the package to generate bindings. So you end up putting all of that into your container, and then you don't just want to put that whole thing into production, because we don't want any unnecessary code running in production, and we certainly don't want any code in our SBOM that makes it appear like we have a larger risk profile than we really do, because we're never running that code. So we have a cleanup script that runs that just searches through the whole file system of the container, deletes anything called test or things like that. And now for the last point here about profiling, I talked very briefly about profiling before, but we're going to go more in depth now. We tried the Profile.jl standard library, Tracy, and Intel VTune. We found VTune to be the most helpful because of all of the features that it has. It supports a variety of programming paradigms, including multi-processing, so it can profile an entire process tree, like if you're using distributed or something, a variety of hardware, and it scales really well as you have huge numbers of tasks. It's like our analyzer will spawn around 50,000 tasks over analyzing one measurement. And Profile and Tracy really don't scale well with that many tasks. But the biggest problem with it is lack of documentation. We do want to address that. I have some later points about that, but you may have a bit of a hard time getting up to speed with VTune because of that. But I do have some notes to hopefully make that easier. One is you may want to build Julia with that flag in your makefile. It's not required, but it can give VTune some extra information that can help you out. And I have seen at least one case where VTune failed to finalize a profile because I did not have that flag. It shouldn't be necessary, but try to recompile if you can. What is necessary, though, is running Julia with this environment variable. Otherwise, VTune will have no idea what is going on with your code, with codes popping out of nowhere at runtime because of the JIT. So you do need to run with that environment variable. And then there's this great package called Intel ITT. VTune will let you start profiling your application in a paused state where it will initialize everything and then wait to start collecting data. So if you have a warm-up period or compilation that your code has to go through first, you can use that package to tell VTune to resume collection whenever your code is ready to actually be profiled. And then a quick note about avoiding hardware sampling, because I've heard at least one case of it breaking somebody's computer, and it has a pretty finicky kernel module you have to use, and really 99% of the time you don't need it. So just to illustrate how we used VTune and to give you all a very brief introduction to it, I've extracted the part of our analyzer that was being slow into this example. What this does is we have a @threads for loop, and on each thread we create an FFT plan and then use that to filter an image. We found that this was being pretty slow, so if we look at it in VTune, this is what the interface looks like. If we zoom into that, then we can see there's this function plan RFFT, which is dominated by another function called Julia slow lock, which, as the name implies, it's taking a lock, which really, that doesn't seem right because the plans should not have any dependencies on each other based on that code. But actually what's going on is the FFTW planner is inherently single-threaded. So therefore, any call to make a plan is protected by a lock, even though we can't see it, but we see it here in our flame graph. So if we instead refactor that plan to outside the loop and then reuse it on each iteration, we should do a lot better. And here's that profile. Now that pink section is plan RFFT, and it's so quick that it's not even worth zooming into. So great, we fixed the bottleneck. Hopefully this gives you a brief idea of what VTune looks like. And now Ian can talk more about how we actually did that optimization.
Yeah, so the actual change to image filtering is available at that PR if you're interested. The main thing I want to talk about is that I think it's nice to sometimes float some of these issues up to the surface, and I consider the surface to be the @time macro. And so this was actually an example of why, or this is the exact case, which prompted me to propose that we add the lock conflicts to the @time macro, so that users can be told when locks are contending and you're potentially having design issues.
So just to summarize this stuff with profiling, we basically recommend VTune to anyone that is profiling their Julia code, especially if, like us, you have very high task counts. There are a ton more features to VTune than what we showed, so please go take a look and explore that. And basically, we're going to take what we learned in this process and try to improve Julia's docs so it's easier for all of you to get started with it.
Yeah, and then we're just going to finish up with some gripes in the spirit of the gripes channel on Slack. So for us, originally, pre-compilation used to take too long, and that was why it was actually pretty critical for us to speed that up. So that was a big motivator for myself to implement parallel pre-compilation. But I say kind of because now that it's parallel, I think more stuff is being pre-compiled. So we're kind of using up the time that we saved, which is, so I'm excited about the work that Stefan has designed in potentially putting package images up in the package server and reusing those. The other thing was that for us, CI was just so slow that we couldn't. That CI with coverage was so slow that we just couldn't use it, and that was a motivator to fix that. So now, if you run CI with its default configuration from package.test or the Julia run test action, it will only generate coverage for your package, and that's a lot faster now. And then a more recent thing, which Curtis helped with, was that we were finding that we would just every time we ran CI, it was pre-compiling, and it was because the Julia cache action, which has been around for a while, never cached package images because there was a couple of details I won't go into right now, but they're now fixed, and it means that you can actually cache your package images, and I really recommend that people add that action. And we are talking about maybe adding that to the setup Julia action as a default, so that could be something to consider. And then another thing is that for us, we'd love to be able to use some ARM systems, Linux ARM systems, both lower power machines, but also in the AWS infrastructure. They're more cost effective. But because Linux ARM is tier 2, we don't quite have the confidence to do that. And I know that there are some issues remaining there. And then the great thing that would really kind of instill some more trust is to do like a package eval run on Linux ARM. So we're happy to help that along.
Yeah, and then about the test standard library, test is really simple, and in all due fairness, it's really good at the limited number of things that it does. But some users, especially like companies like us, need some more things. Like we really need parallel evaluation of tests, both threading and multiprocessing, and we need to generate test reports in multiple formats. The text format's great for seeing in CI, but like we need to take test reports and put them into our QMS, for example. So we need like other formats like JU to XML, for example. So if any of you feel similar, please do get in touch, and we can collaborate on that. Next, I talked briefly about what happens when you install a package. You get the whole source tree. This also affects like cloning with monorepos. So if you clone 5 packages from the same monorepo, you get the whole monorepo 5 times. And then you need to clean up all of those files. It's not totally clear what we can do about this, like if we could ship artifacts or something like that. But if you feel similarly, then please get in touch and we can brainstorm something. Next, the dependency confusion issue. Unfortunately has been open for 3 years now. Stefan proposed a pretty well thought out plan for what we can do about that, and there wasn't much community disagreement with it either. The issue just sort of fizzled out, unfortunately. So we would like to call more attention to that and hopefully get a fix for that. In the meantime, I do have a tool there called Registry Scanner, and I would encourage any of you that run private registries with private packages to run Registry Scanner and just make sure that no one is trying to do this attack against your organization. And then quickly about JLLs, we have had to test lots of unreleased JLLs throughout this process, and doing that is a ton of work, a lot of manual work, so we're working on some automation to make that easier.
Yeah, and then so highlighting lock contention in that time, that's solved. But in a similar spirit, and something that actually has come up in this JuliaCon, and I have a PR open for it, is an idea to expose in at time when too much time is being spent in the scheduler. So for instance, there's kind of the classic case of whether you do at threads 4 or 4 at spawn. So just spawn a load of tasks or get at threads to do something that's a bit cleverer. And it can kind of not always be obvious that you're making a mistake in like spending too much time in the scheduler because you have too many tasks that are too short. So this is a PR that's open as of yesterday. I think the metric needs some work. We need to figure out what the right threshold is. But if you can see in the bottom right, we're reporting that this case with the busy equals false, so just at spawn nothing, spends like 60% actually scheduling and not doing any real work. So yeah, that's just something purely work in progress. Yeah, thank you very much.
Thank you very much for the very interesting talk. We will now have a 10 minutes break before the next keynote speaker. So just to note that the keynote is at 10 past 5, not half past 5, as was mentioned in the slide, so in 10 minutes. And meanwhile, if you have questions for the speakers, feel free to reach out to them. See you in 10 minutes.
Thanks.
Thanks.